Suppose V is an inner product space, and suppose V1, V2 to Vn are vectors in that inner product space, such that whenever I take the inner product of Vi with Vj, I get 0, whenever I is not equal to j. Then the set of vectors V1 through Vn is called an orthogonal set of vectors. And you can see that every pair of vectors in the set is orthogonal. Let's look at an example. So let's say we have these three vectors in R3. 1, 1, 1, 2, negative 6, 4, and negative 5, 1, 4. And I want to show that they are an orthogonal set of vectors. So this is an orthogonal set. So what do I need to show? Well, if we call this vector V1, this vector V2, and this vector V3, then I need to show that the inner product of V1 with V2 is 0. The inner product of V1 with V3 is 0. And the inner product of V2 with V3 is 0. That's the definition of an orthogonal set. Every pair of vectors, when you take the inner product, is 0. And we don't have to worry about flipping these around, saying something like V2 with V1, because we know that the inner product is symmetric. Okay, let's start with the first one. Let's take the inner product of V1 with V2. Now, unless it's specifically stated, the inner product we're going to use in Rn is always going to be the first one transposed times the second one. This is the general inner product in this case is R3, but it works for Rn. So if they're not using this inner product, they'll say it in the book or on the homework or on a test. Okay, so let's see. V1 transpose is 1, 1, 1. And V2 is 2, negative 6, 4. If we multiply these, we get 2 plus negative 6 plus 4, which is 0. So that works. Let's try the second one. The inner product of V1 with V3 is 1, 1, 1 with negative 5, 1, 4, which is negative 5 plus 1 plus 4, just taking the dot product, and this is negative 5 plus 5, which is 0, so that works. Now let's check the last one. The inner product of V2 with V3 is 2, negative 6, 4 with negative 5, 1, 4, and that is negative 10 minus 6 plus 16, that is also 0. So you see that we have an orthogonal set of vectors. Now we can take this one step further. An orthonormal set of vectors is an orthogonal set of vectors where each vector in the set is a unit vector, meaning that it has length 1. So, and here we're going to be using the norm being the square root of the inner product of a vector with itself. If we're using a different norm, it'll be stated. Okay, so let's look at an example. Here we already showed that this set is an orthogonal set of vectors. We want to make this set an orthonormal set. So if this is V1, this is V2, and this is V3, well, all we need to do is divide each vector by its length, and that's just multiplying a vector by a scalar. So here, if we take V1 and multiply it by this scalar, we're not changing the direction of the vector, because this is going to be a positive number, 1 over a positive number. It's not going to be 0 and it's not going to be negative. So it's in the same direction. So it's not like changing the angles between these vectors. It's just changing the length. So that's what we're going to do here. So let's figure out the length of 1, 1, 1. So if we take the inner product of V1 with itself and then take the square root, this is the length of V1, and that is the square root of 1 squared plus 1 squared plus 1 squared, which is the square root of 3. If we take the length of V2, we're going to get the square root of 4 plus 36 plus 16. That is square root of 56. I'm not going to simplify that radical. I'm just going to leave it like that. And then the length of V3 is the square root of 25 plus 1 plus 16. Oh, that is 26 plus 16, which is 42. So now I know the lengths of all these vectors, so I'm just going to divide by the length, and then I'll get an orthonormal set of vectors. So let me erase this. I'm going to leave these numbers right here. I did them in order, so it shouldn't be hard to figure out who they belong to. So we can say the vectors 1 over square root 3, 1, 1, 1. And you can also leave it in this transpose notation if you like. 1 over the square root of 56, 2, negative 6, 4. And you can send that into every entry if you like. And 1 over the square root of 42, negative 5, 1, 4. This is an orthonormal set of vectors. They all have length 1, and if we take the inner product of each one, we'll get 0. So something to note is that a set of vectors V1, V2 to Vn is orthonormal if and only if the inner product of Vi with Vj is delta Ij, where delta Ij is 1 if I is equal to j, and 0 if I is not equal to j. So if we take a vector and we take the inner product of the vector with itself, we get 1. And if we take a vector with any other vector besides itself, and we take the inner product, we get 0. So if I give you a set and I ask you if it's orthonormal, if it doesn't satisfy this condition, then no, it's not orthonormal. Our next topic is orthogonal matrices. So we can take this idea of orthonormal vectors and use it for something called an orthogonal matrix. So putting that with matrices. So let's let Q be an n by n matrix. We're going to call this matrix orthogonal if the column vectors of Q form so they're linearly independent. So they form an orthonormal basis. So we're going to have this matrix Q is going to look like, it's n by n. So it's going to have n columns. And we want the inner product of these columns, AI with AJ, to equal delta IJ. So if it's A1 with A1 or A2 with A2 or so on, we get 1. But if it's A1 with A3 and so on, we get 0. So we have n columns and the columns themselves are orthonormal. Okay, and notice that I use the word basis. It's an orthonormal basis for Rn. So let's put that here as well. That means if this is a basis for Rn, the rank of the matrix is going to be n, which tells us, and this is a square matrix, which tells us it's invertible because it's going to have n pivots. And we can actually talk about what the inverse is. And this is actually really neat. So if you have an n by n matrix and Q is orthogonal, this is true if and only if the inverse of Q is actually its transpose. So how do we prove that? Let me actually let it sink in for a second. If the transpose of a matrix is its inverse, then the columns in that matrix form an orthonormal basis for Rn. Okay, so let's think about how we can prove this. Again, when we say orthogonal, orthonormal, we're talking about an inner product, and here the inner product's not specified, so we're assuming the inner product of two vectors, x and y, is x transpose times y. Okay, so you need to remember that that is the inner product. We're going to talk about the proof. We're not going to do this in great detail, but let's say Q is orthogonal. So that means Q is equal to A1, A2, AN, where the inner product of AI with AJ is delta IJ. But what is the inner product? That's AI transpose times AJ is delta IJ. Okay, well, that means I'm taking AI, which is a column, and now I've written it as a row. So this is now, this is going to be a row. So let's say A1, I'm going to write it like that. And then I multiply it by the column A1, and I get 1. And then I could take so what I'm trying to get at is if you think about the transpose of Q, which would look like A1, A2 to AN, and if I multiply it with Q, which is A1, A2 to AN, what would I get? Well, we're taking a column which has the same number of entries. This is the column, this is the row, we just flipped it, so we can take the dot product. And if we take the dot product, that would correspond to the 1 in the 1, 1 position of this new matrix. But if we take this, which was a column, now it's a row, and this is the transpose of that column A1, and we're multiplying it with the column A2. But that's just the inner product of A1 with A2, and by definition is going to be 0 because 1 is not equal to 2, so we get 0. Then if we take this row A1 with A3 all the way to AN, we get a bunch of zeros. If we take A2 and multiply it with A1, this is A2 transpose times A1, so we get 0. And then A2 with A2 would give us 1, just by using the definition of the inner product here, and 0 for the rest. And we actually get the identity matrix, the n by n identity matrix. So you can see that this is the transpose of Q, and Q's n by n. So the transpose is n by n, and we're taking an n by n matrix, multiplying it by an n by n matrix. We're going to have an n by n matrix. And you can see that the inverse of Q is actually just the transpose. So that's really interesting. So something I could ask on a test, I could say, I could actually tell you this. I could say, the inverse of Q is its transpose. What can you tell me about the columns in the matrix Q? You say, oh, well, first off, because the Q is invertible, they're linearly independent. But even more than that, you can tell me that the inner product of each vector with a vector other than itself is going to be 0, and the length of each vector is 1, so the column vectors. So it's an orthonormal basis for Rn. And I could also say, oh, here's an orthonormal basis for Rn, put it into a matrix. What is its inverse? And you might think, oh, I got to do a bunch of work, but if you knew it was an orthonormal basis, you just take the transpose and then you would be able to give me the inverse. So let's sum up the properties of orthogonal matrices. So again, an orthogonal matrix is a matrix that has for column vectors, now this is an n by n matrix, the column vectors form an orthonormal basis. So let's write that. The first thing is the columns are an orthonormal basis for Rn. The second thing is that the transpose of the matrix times the matrix is the identity, which tells us that Q inverse is actually the transpose. But something else I can tell you is that if we take a vector x that's in Rn and multiply it by the matrix, we also get a vector in Rn. And if we take another vector y and multiply it by the matrix, well, this is going to be equal to the inner product of x with y. So it's like you didn't even have to multiply by Q to begin with. And why is that? Well, here we are missing a step. You can say that if you remember back in the day, we said that if we have a matrix here, this is equal to putting the transpose on this side. But if I take the transpose for what we have, so qx qy is equal to x qt qy, but this is just the identity, so that's how I get this piece here. Okay, and then the last thing we're going to say is that the length of the vector q times x, now this is the norm, the normal length of a vector. So remember that the length of some vector y, this is our normal length. You can write that, but I'm just going to skip that. It's the square root of the inner product of y with itself. And this is going to be just equal to the length of the vector. So we don't even have to put the q here. Multiplying a vector by q, if it satisfies these properties, you know that q transpose times q is equal to I, you just don't even have to multiply by q. And that's also an easy proof, because this is equal to the square root of qx with qx, and by this last property, this is the square root of x with x, so this is just the length of x.